ছাৰ আপুনি ষ্টাৰ্ট কৰিব পাৰিব মই এইটো ৰুবলৈ গৈছোঁ
Good morning to you all. Let me start again. We stopped, I think, here when you said Ganymede has a magnetic field, and is the, I think this is the largest moon of the planet Jupiter. I think not only of the planet Jupiter, but all of the planetary systems. This may be the largest moon. So it has characteristics also is that it has magnetic field, and since it has a magnetic field, as we have shown that it has a magnetosphere, only point is that it doesn't have the boson in front of it because of the flow of plasma coming out of Jupiter because of the centrifugal force is not supersonic, it's subsonic, and therefore there is no kind of boson here, but it has the connection of magnetic field. Interestingly, the magnetic field of the Jupiter is such that the north pole of the magnetic field is similar to the north pole of the zodiac north pole. Now here, in the case of the moon, it is almost opposite, and it makes 176 degrees, and therefore almost opposite to that, and there is a possibility of uh, the connection being taken place. Anyway, so I think we leave that. We can go to something else. But before that, I said there are three interesting moons of Jupiter. In one orbit of Ganymede, the moon Europa makes two orbits, and the moon Io makes four orbits. That means in each orbit of Ganymede, they are end up that they are all aligned. So they are all aligned every orbit of Ganymede. So that's interesting because there may be a lot of interesting phenomena occurring during that time. So anyway, we leave it there. But we want to go to the aurora, which is a special case in the case of Jupiter. But I could not get a picture of aurora. You can see them in the internet. I could not copy because of the copyright. I tried yesterday, but somehow I missed. Could not do it. I have to take the permission. But anyway, you can see it in the in your internet. There's no problem on that. But only three features I'm just mentioning. One is the main oval. That means if you look from the top in the polar region, the whole of polar region is covered with the um, aurora. In addition to that, there is a circular feature around it, maybe 16 degrees away from the North Pole, and that's the very interesting part. And third one would be the transient one. These two features are almost permanent. That means the main oval aurora and the circular one are almost permanent, except that there are some transient aurora can occur in the oval itself. Now, the transient one could be similar to that of the Earth, because the Earth, we don't have the permanent aurora, they are the kind of transient ones. And that happens because of the fact that there are interactions between the um, magnetosphere Earth and the interplanetary magnetic field. That's the connection at the night side, or away from the surface of the planet, and that gives rise to the kind of aurora which is transient, because that gives the auroral electrojet as well. So that's the same thing happens in Jupiter. The other two things, the main oval is there because the foot of the magnetic field lines connecting the ionosphere of the Jupiter goes to the equatorial plane where there is a disk, current disk, because disk is quite extensive one, and a lot of magnetic field connects to the disk current, and they produce the potential along the magnetic field lines, and the potential actually accelerate the particles. So the accelerated particles flux comes to the aurora and comes to the auroral region and then produces aurora. So that's the oval. And the circular ones is something very special, because here the magnetic field lines which connects the ionosphere of Jupiter connects the main moon of the planet. Maybe there could be two. One is of course the planet Ganymede, other can be even Io. So these are connected with that, and then the connection, sorry, and the aurora that is produced is because of the particle accelerated along the direction of the magnetic field, and that magnetic field should be nearer to the moon. And this acceleration could be, one of them could be the electric field along the direction of the magnetic field, or because of the fact that there are waves in particle interaction along the direction of the magnetic field, which can then accelerate the particles and then produce aurora. There are three things, some more things I can add. This aurora and the uh, kind of magnetosphere of Jupiter can have or belong to all the whole range of electromagnetic emissions, that from the radio to X-rays. So this can happen because of the fact, for example, there are a lot of precipitated particles along the directions of the magnetic field, and these precipitated particles can go farther below to the atmosphere, and in atmosphere there could be molecular hydrogen. When it will interact with the molecular hydrogen, it can produce UV radiation. So UV can be explained. Now, another thing, that when the current flows along the direction of the magnetic field, or the electric goes along the magnetic field, as you can say, the current produces in the ionosphere, and this current with the collision can dissipate. When they dissipate, they produce the heat in the system. When it produces heat in the auroral ionosphere, then that produces infrared. So there are a lot of possibilities of having the emissions in the auroral region, and they can be seen in the whole range of electromagnetic radiation. So I think I'll stop here for the magnetosphere of Jupiter and go to the next one. Next is Saturn. Saturn, well, initially the Voyager 1 and 2 observations were there. It is rapidly rotating dipole. It is quite unique in the sense that there is no tilt of the magnetic axis, and it is very, very symmetric one. So therefore, some people even think of the generation of the magnetic field mechanism could be different, but this is not probably true. The Saturn has the core, and that core is metallic hydrogen, similar to that of the Jupiter. Jupiter also has the core fluid, which is metallic hydrogen and not iron like the one that we have in the case of Earth. There is a departure from the other one is a lack of co-rotation of the magnetospheric plasma. That is because of the fact, because maybe there could be a strong eddy diffusion in the upper atmosphere. Many internal sources of neutrals and charged particles are there because it has many moons around Saturn. And you can see that the Saturn's atmosphere have Titan atmosphere, rings, icy satellites, Mimas, and Enceladus, and so on and so forth. So many of them. And Enceladus, it should be similar to Io. It has a lot of ionosphere, which then can give a lot of plasma to the Saturn atmosphere. And there are one or two things I can add. The Saturn atmosphere can be divided into several different divisions because of the fact that there are the rings. Say, for example, it has a small radiation belt because of the fact that there are rings which does not allow to have the particles of the type that we have in radiation belt. So the radiation belt is nearer to the Saturn atmosphere. It could be near the 3RS radius of Saturn, where the a lot of main rings is there. So the radiation belt could be produced there. Now, since there are a lot of moons having this atmosphere around it, some of them are partially ionized. So the moon, so the rings of Saturn has ion structure of spokes because of the fact it has dusty plasma. The characteristic of dusty plasma done, some studies were done and showed that the spokes-like structure can be obtained because of the dusty plasmas. Wave interaction can take place and because of the Western mode wave and cyclotron wave near the orbit of Dion. Saturn main aurora, as I said, is driven by the solar wind. That means it is coming because of the solar wind interaction with the magnetosphere of the Saturn, and that reconnection takes place at the night side of the magnetosphere, which then produces energetic electrons because of the electrostatic potential along the direction of the magnetic field. So that is a kind of satellite Saturn magnetosphere. Does not have too many different characteristics, almost similar to that of the Earth. Let's go to the Uranus. Uranus is a kind of satellite which is spin axis directed towards the sun solar ring or towards the sun. So that is a very special feature. No other planets have spin axis pointing towards the sun. So obviously, if the planet has normal kind of magnetic field, that means a dipole magnetic field having north pole towards the north pole, geometric north pole, then one would have expected a pole on magnetosphere. That means the polar side is on the sun side and they can produce magnetosphere which would be rotating around. But that is not the case because there is a sun surprise, and that surprise is that the tilt of magnetic field is very large, almost 60 degree with respect to the spin axis. As you see in the picture, the magnetic field and the spin axis is towards the sun, but magnetic axis is at an angle of 60 degree. And not only that, the whole sort of magnetic field is shifted or center is shifted about 1 3 radius of Uranus, that is away from the sun, and this is called offset tilted dipole. Now dipole looks like the one that is shown in the picture, and it rotates. You can think of the rotation which is toward the sun, and the such an asymmetric uh, magnetic fields around the rotation axis. So it will produce at certain it produces the magnetosphere instantaneously because that is the instantaneous picture of the magnetic field of the Uranus, but it will vary as it rotates around. But at one stage it will be like that. If it is like that, then it produces the magnetosphere. There would be a tail on the right side, and there would be the convection, and convection the plasma will come in. But only difference is that now the plasma, when it comes in, it does not see the effect of rotation because they are orthogonal to each other. So it does not oppose the plasma convection velocity towards the surface of the planet. So the whole of convection can come near the surface of the planet, and the result is there cannot be any plasma pulse, there cannot be any plasma sphere. These are two important things for the Uranus, that it does not have plasma sphere, and the convection electric field can come very near to the surface of the planet. What are the third thing? That if you rotate, if you see the rotation of the magnetic field of the planet, then at one stage you would see that there may not be any reconnection. So the magnetosphere which is generated by the reconnection process will not be there. So therefore, this would be kinds of magnetosphere could be switched on or switched off because of the rotation of the planet and the peculiar structure of the magnetic field. So this is something surprising aspect of the Uranus magnetosphere. So this is shown, the magnetosphere is shown like this. As you can see that in this particular situation, the magnetosphere could be of this different style, this different part, but in some point there could not be any reconnection, and then you can get a magnetosphere of may not get a magnetosphere at some state. So let's go to the Neptune. Here, of course, the planetary rotation axis is not is normal as a tilt, but it is not towards the sun like Uranus. It has a magnetic axis, and the planetary rotation axis here also is not actually with the magnetic axis. We can see that in the below. Assuming that there is no appreciable tilt, a normal Earth-like magnetosphere is expected. Assuming that the magnetic field that is generated in the planetary in the planet of magnetic planet Neptune, we would see the normal magnetosphere like that of the Earth. However, here also there is a surprise. What is the surprise? It is the same kind of surprise that there is an unexpected large tilt of about 447 degree. So there is a tilt of the rotation axis compared to the magnetic axis by 47 degrees. Not only that, you can see the dipole, the magnetic field, is not the same as that of the Earth. It is shifted toward the south, almost half of radius of the Neptune. So magnetic field configuration can be seen in the picture as I shown on the right hand side. So something very peculiar. Now the question that would be asked that the whole of the magnetic axis would be exposed to the sun, whether it is rotates, even if it rotates, rotation axis you can see like that, it is not along the direction of the sun or toward the sun, so it rotates, so the almost all the time one part, the pole of the magnetic field is looking toward the sun. So whatever magnetosphere is bodies, we call is the pole-like magnetosphere. Polar magnet. It brings variability in the configuration of a magnetosphere. That is a surprise. Dipole axis changes its orientation considerably during the period of rotation that we can see. When Voyager entered the magnetosphere, dipole axis was parallel to the solar wind direction. The dipole axis was actually parallel to the solar wind direction. So therefore, the polar cap was completely exposed to the sun. And therefore, if the magnetosphere is there, that becomes polar magnetosphere. So depending on the phase of the magnetosphere, the magnetosphere itself changes from polar to Earth-like. So this is an important aspect of the magnetosphere of Neptune. And it is seen here on the left hand side, you can see the cusp is completely towards the direction of sun direction, and you can see the pole magnetosphere. While on the right side, it comes as the normal sort of magnetosphere, and this happens because of the rotation and the configuration of the magnetic field axis with respect to rotation. So these are the two, this is one of the important aspects of the Neptune magnetosphere. So this is the end of the magnetosphere of the planet having intrinsic magnetic field. Now let's go to the magnetosphere of Venus, which does not have any intrinsic magnetic field, and it has, so there will be no solar wind interaction with the planet like the one that we have in the case of magnetic planets. Okay, two important quantities. One is the substantial ionization, which is produced by extreme ultraviolet, and that produces the high thermal pressure. And that high thermal pressure could be sometimes greater than solar wind dynamic pressure. And this thermal pressure is um, radial distance dependent. So at certain time, certain area, certain space, the solar wind dynamic pressure could be small compared to the thermal pressure. So the whole solar wind dynamic pressure may not go completely near the atmosphere of the Venus. Another important aspect is there is a cap forms in the ionosphere. Do you know what is the cap from? Cap is produced because of the fact there is a magnetic barrier. Why there is a magnetic barrier? A lot of plasma come, try to penetrate the atmosphere of the planet. Now there could be a boundary because a lot of magnetic field comes and they are accumulating there in the front. When they accumulate, they produce a magnetic energy, and there is of course dynamic pressure, solar wind pressure. At time, this solar wind pressure could be equal to the pressure of the magnetic field because of the compressed one or the barrier one, so they could be similar. But this magnetic pressure would then try to press the plasma or the ionized particles of the planet's ionosphere. So there could be a boundary between these two. If the boundary happens to be in the collisionless region, then there will be a sharp boundary between the magnetic barrier and the ionosphere. So that's how you can produce a magnetosphere of the planet Venus, which does not have magnetic field. However, it is produced a cavity because of the magnetic barrier. Now, this is an ideal case of the uh, magnetosphere of Venus, but there could be something very interesting one, which people can just postulate, can think that when this boundary is produced in collisionless regime, then there is a sharp boundary. Now, if the solar wind dynamic pressure happens to be such that it becomes more than the magnetic pressure of the magnetic barrier, then this can be magnetic field can be pushed inside the ionospheric plasma, and it can go down to the region where there is collisions. Now, when this magnetic field goes down in the region where there exist collisions, then the diffusion can take place of this magnetic field in the collisional plasma, and then the magnetic field can decay. Now, in that case, what happens to the magnetic field? Well, magnetic field can decay, and it can be in the ionosphere as a kind of memory. So this is a kind of thing people think of, but the magnetosphere is observed by the different new satellites which goes around Venus, which is called say Pioneer Venus orbiter, uh, and this magnetic barrier that I talked about, is because of the fact that I said the interplanetary magnetic field get accumulated there, right? And then produces magnetic pressure. Now there is something else can also happen. What is that happen? What is that something else? Something else is that the magnetic field of the interplanetary medium can be time dependent. When it is time dependent, that it produces a potential, electric field potential by our Maxwell's equation, C curl of B is equal to minus dB dt. So that produces extra magnetic field because of the time dependent uh, magnetic field of the interplanetary medium, and that can add them up in the barrier, magnetic barrier, and in that case, magnetic barrier can be even stronger, and then the situation that we talked about may not happen. So anyway, these are certain things which is associated with the Venus magnetosphere. Well, this already I have already said almost everything there. Well, as far as the magnetosphere of Venus is concerned, it, it is becoming even more complicated than that of Jupiter, because of the combination of the uh, iron, ionized particles around the planet, which has several kind of dynamics taking place. It can mass loading effect, and then the mass loading effect can uh, be such that it produces, when the tail will have the mass from the planet itself, because it goes along the magnetic field lines on the front side of the magnetosphere. And there are a lot of other things which can be there because of the ionosphere. Now, well, this is not very important in the case. I said there is an expression I've written, which is actually is the determination of the ionopause. Ionopause is determined by the balance between the solar wind dynamic pressure and the pressure associated with the atmosphere of the planet itself. Right hand side you see that is the expression that you can obtain from the atmosphere of the planet, and that you have also seen in the case of, even in the case of atmosphere of the sun, when it is kind of equilibrium or static equilibrium, then you can get this kind of pressure on the right hand side, and left hand side is the pressure associated with the solar wind, and this expression is quite familiar to you. When they are equal, then they produce a boundary, and that boundary is a kind of ionophores. So let's go to the magnetosphere of Mars. Magnetosphere of Mars is not very similar to Venus actually, because Mars has some magnetic field, which is a crust magnetic field, and they can produce some kind of magnetic field around the planet, and that can produce a bow shock and can also produce magnetopause, and these are actually observed, and can produce day side, night side ionosphere magneto tail. magnetotail can be produced, where the kind of tail we can get in our magnetosphere of the Earth. But anyway, it is weak intrinsic magnetic field. So there can be two things. Uh, when there is a solar wind interaction with the magnetic field of Mars, then we can see that a magnetosphere on the left hand side can be obtained. There could be a magnetopause, there could be day-side reconnection, and so on and so forth. But if solar wind is, or the sun is very active and solar wind velocity is very large, or maybe CMEs which are produced, then that picture is not valid, because it does not, magnetic field is sort of cannot really oppose the pressure driven by the sun, and then it produces something like the one that is shown on the right hand side. On the right hand side, it, it can have the one can have, of course, Borsuk. Then there could be flux group get into the atmosphere of Mars. These flux groups is associated with the Siamese, and some of them can go inside and can remain there. But that is rather complex picture. I don't want to go into that detail at the moment. Um, and we go to little bit of new observations that Marvin, a satellite, has some more observation, because that satellite has gone to the orbit around the planet in the September 2014 and obtained a kind of map of the weak magnetic field around Mars. So it looks like that the Mars magnetic field is produced around the around the planet Mars, and which is called the induced magnetic field. This induced magnetic field is actually generated by the solar wind and non-magnetic planet. What does the solar wind do? The solar wind, as it moves, so far as the conducting medium is highly conducting, it produces an electric field, and that electric field moves along with the plasma. Or in other words, the magnetic field lines is kind of frozen in. But when it comes near the atmosphere of the Mars, and there is some uh, ionized particles around Mars, because of the fact that our ultraviolet, solar ultraviolet and other thing produces ionization, so they are ionized, and when they are ionized and non-ionized particles, there are collisions, and therefore the conductivity in that region will not be infinite conductivity. When the plasma goes through it, magnetic field goes through it, and magnetic field is not really frozen in now. It sees the non-conducting medium, and when it sees the non-conducting medium, it produces an EMF, and that EMF produces a magnetic field. It is something like a dynamo, and that magnetic field is there around the planet Mars. So this is the contribution of the observation that is given by the planet. So therefore, you produce the current around the Mars atmosphere, and that current produces magnetic field, and that magnetic field makes the planet as induced magnetosphere. So that is the kind of magnetosphere that the new observation is suggesting to us, that it is the induced magnetosphere, and it is because of the interaction between the solar wind with the planet's atmosphere, and the reason being given is that there is a current around it. Now, therefore, this is the magnetosphere of it produces a magnetic field and it produces magnetic field, then we get the magnetosphere of our normal kind within including tail and everything. So that's the new kind of idea or new kind of information that we have. So now there is something very interesting thing came out of it. People were thinking about it. Then a lot of people would go to Mars and they would like to live in there and they would like to make the magnetic field around it so that their life in the Mars, in the atmosphere of the Mars, would remain a little bit more comfortable or safe. So they would like to have magnetic field around it. Now the point is, could we produce magnetic field around it artificially? Then the interesting idea is that the Phobos is one of the moons of Neptune, sorry, this Mars, and Phobos goes around Mars, and these Phobos, as the ionized particles, it goes around the planet, so it can produce some kind of current by the Phobos, and then it can produce the magnetic field. So that probably people can think about it that if you can do that, then artificially you can produce the current around it, and then it can produce magnetic field. So that is the interesting thought. Anyway, so I that's um, such mention it, thinking that it is kind of interesting one. So anyway, I think I have. This is the end of my talk on the magnetosphere of the outer planets. I've included all the planets with intrinsic magnetic field, also included the planets without magnetic field, like the one that we call Venus and Mars. So I think I have also consumed all my time, and therefore I would like to have some questions if you have. And if I can, I'll answer them.
Yes, sir. Yes. Okay. So students are requested to go for questions if you have any.
Good morning, sir.
Good morning.
Sir, my question was, you were showing in some of the earlier classes you have shown in one slide. Actually, in this slide it was equation number 5. There you have derived the equation considering the three Maxwell's equation.
Yes.
There, the curl of B is equals to that 4 pi j term. It is in CGS unit, right? I
Yes.
have tried it in actually in MKS unit. So now my question was, if we write it in MKS unit, it is curl of B is equals to mu naught J plus mu naught epsilon naught del E del T, right?
Oh, it should not depend upon the unit that you have used. It should come out, maybe the expression of xi would be some, because the c will not be there in your equation, and therefore the equation would be coming because of the that the you take the curl to both sides and you get the curl of b, and that you can certainly use your vector algebra, and then that comes out to be del square of b, which will be coming like that. Certainly, there would be the only difference would be in expression of your um, the diffusion coefficient, or there would be there are some other
Complete one.
constant which will be coming there. And
Yes,
even
sir, but my question was actually that why didn't we consider that Delhi Delta term in the curl of E expression? That was actually my question.
what did-
In
in
the curl of B term, in the curl of B expression, it is like we have two terms, right? Mu naught times J and mu naught epsilon naught Delhi Delta, right?
yes,
So why we are not considering that Delhi Delta term in equation 2? You haven't mentioned that actually.
well, I have not